Hi, in this video we will see that L'Hopital rule can be applied when we have one-sided limits or when we have limit at infinity. Well, recall that the L'Hopital's rule can be applied when we have two differentiable functions, f and g are differentiable. And f over g makes sense in a neighborhood of a. It means that, well, you can write f prime over g prime. Also, you need to have an indeterminate form of type 0 over 0. So it means that the numerator and the denominator have a limit 0. Then you can apply L'Hopital's rule, which says limit of f over g as x approaches to a is equal to limit of f prime over g prime as x approaches to a. And the remark is that this not only works for limit as x approaches to a, also it works when you have one-sided limits. So the L'Hopital's rule works also for limits when x approaches to a plus or minus, or when you have x going to plus or minus infinity. So whenever you have infinite 0 over 0 indeterminate form, you can apply on and this condition, which is differentiable. You can differentiate, then you can apply L'Hopital's rule. Okay, so let's see some examples here. We have tan x minus x over x cubed plus x to the power 4 as x goes to 0 plus. Okay, first thing is that try to evaluate numerator and denominator separately, and you get 0 in numerator, 0 on the denominator. 0 over 0 is not value of limit. It just says that this is 0 over 0 indeterminate form, and then since the numerator and denominator are differentiable functions, we can use L'Hopital's rule, meaning that the limit of the original limit will be equal to limit of the quotient when you replace the numerator by its derivative and the denominator by its derivative. Very nice. Now we have a new limit, and we can again check the limit of the numerator and denominator separately. Again, you get 0 over 0, and since the functions are differentiable, we can use L'Hopital's rule, and that will give us the derivative of 2 secant x squared is 2 derivative of secant, which is secant x times tan x, times secant to the power 2 minus 1. So that means that there will be another secant. That's why I can write secant squared here. And this will be 6x plus 12x squared. Very nice. Now plug in the numerator and, well, or find the limit of numerator and denominator as x goes to 0 from the right. And again, we will see that the limit of numerator is 0, limit of denominator, and we can apply L'Hopital's rule. So L'Hopital's rule, I will replace the numerator by the derivative of numerator. So product rule, this will give us 4 secant squared x tan squared x. Derivative of secant squared itself is secant squared tan x. There's another tan that will give us tan squared, plus 2 times secant squared x times derivative of tan is secant squared. So together we get secant to the power 4 and 6 plus 24x. Very nice. But when you get to this point, you see that the limit of the denominator as x goes to 0 is a non-zero number. So this will be 0 plus 24 times 0. And, well, you then compute the limit of the denominator and use the quotient law. 4 times 1 squared, tan of 0 is 0 squared, plus 2 times secant of 0 is 1 to the power 4. So this will give us 2 over 6, which is just 1 over 3. Very nice. How about this one? Okay, so here, well, I have a typo here. This needs to be plus. When you first try to see the limit, you notice that the limit of the denominator as x goes to 1 from the negative side, from the left you get 0, and from the right you get 0. So we can use the Labtube rule because the functions are differentiable, and what you will get is 3x squared minus 8x plus 2 in the numerator, 5x to the power 4 plus 6x in the denominator. And now when you find the limit of the denominator, you get 5 plus 6 times 1, and 3 times 1 squared minus, that's a non-zero number, so that's why you can use the quotient law, and this will give us 11 in the denominator. In the numerator you have 5 minus 8, which is negative 3. So the limit is negative 3 over 11. And as I mentioned in the remark, this will also work when x approaches to plus or minus infinity. If we have indeterminate form, you see as x approaches to negative infinity, e to the power x approaches to 0, and e to the power x is 0, 1 plus 0 is 1, limit ln of 1 is 0. So we have 0 over 0, and then we can use Labtube's rule because these are good functions, differentiable functions. And as you can see, the numerator, I can replace it by its derivative, which is again e to the power x. The denominator, derivative of u is u prime, so derivative of 1 plus e to the power x is 0 plus e to the power x, u prime over u. Before we do find the limit again, we try to simplify a little bit. So 1 plus e to the power x, e to the power x, e to the power x. As you can see, both of them have the factor e to the power x. We can cancel them and we get limit of 1 plus e to the power x as x approaches to negative infinity, and this is nothing but 1 plus 0, which gives us 1. So Labtube rule will be possible to be applied when you have one-sided limit or limit at infinity, and the conditions of the Labtube's rule are satisfied, meaning that we have indeterminate form of type 0 over 0, then you can go ahead and use Labtube's rule.